We're going to be looking at lesson 1.6, which is solving inequalities. We actually first start with a little investigation of linear inequalities. This is going to look similar to some of our properties of equalities or of equations. But what we do is we just use this true inequality that 2 is less than 10. That's definitely a true statement, and we're going to fill in this table. If we add 7 to both sides, 2 plus 7 is 9, and 10 plus 7 is 17. Is 9 less than 17? It is, yes, so we still have a true statement. Well, what if we add -4, which is the same as subtracting 4 from both sides? Back to our original, it's 2 minus 4, or plus -4 is -2, is less than 10 plus -4 is 6. Is this still a true statement? -2 is less than 6? It is. All right, what if we multiply both sides by 3? 2 times 3 is 6, and 10 times 3 is 30. Still a true statement. As we walk through each of those, we could add things other than 7 and realize it will be true, things other than 4. We can multiply by other numbers other than 3, but then now we're going to multiply both sides by -4. 2 times -4 is -8, and -4 times 10 is -40, and in this case, -40 is actually less. It's further to the left on the number line, so it is not true. And so when we multiply, what we're trying to see here is when we multiply by negatives, it does not give us a true statement. So what we learn here is we can add or subtract anything from both sides of an inequality and it remains true. And if we multiply both sides by a positive, multiply or divide both sides by a positive, it remains true. But if we multiply by a negative, it is not true. And so therefore what we do is switch the equation of the sign. We have a little table here that explains this. The properties of inequality. We have the addition and subtraction, or addition or subtraction property. If you add or subtract the same quantity to both sides of an inequality, the inequality will still be true. We saw it in our example. We see it here with numbers. We add 2 to both sides. Here's what we see algebraically when we see this as a rule in symbols. We have any real numbers a and b. Where a is less than b, we can add some real number c. So that c, it could be a positive or it could be a negative or a fraction. We can add that to both sides and it will still remain true. Part 1 of the next rule, multiplication and division, if you multiply or divide both sides of an inequality by the same positive number, the inequality is still true. So we have 3 is less than 7 if we multiply both sides by a positive number. So in this example, we multiply by a positive 2. In the algebra terms here, a is less than b. They're real numbers. If you multiply both sides by c, it's still true as long as c is greater than 0, which means it's positive. And the last part 1, which is part 2, if you multiply both sides of an inequality by the same negative number, the inequality must be switched. So we have to switch the direction of the sign. We see that in this example here. We have 3 is less than 7, which is true, but if we multiply both sides by -2, notice we changed the direction of the inequality sign. And then you see it over in symbols where we have a is less than b. They're both real numbers. If we multiply by c, which is less than 0, a negative number, what did we do? Well, we switched the direction of the sign. All right, so that's the rule. So we can solve these 4 inequalities. It says solve and graph, so we'll draw a little number line for our answer. Some questions later on you will have to draw a graph, others you won't. So we have negative 3 times 2x minus 5 is greater than 27. Well, we still can use the distributive property. We get negative 6x plus 15 is greater than 27. We're going to continue solving. We'll subtract 15 from both sides. Well, we can subtract 15. We don't have to change the direction of the sign. The only time we change the direction of the sign is when we multiply or divide both sides by a negative number. 27 minus 15 is 12. And here's one of those cases. And to solve this, we have to divide both sides by negative 6. And when we divide by a negative, we must switch the direction of the inequality sign. So x is less than, and 12 divided by negative 6 is negative 2. There's the answer. We solved it. Now we're going to graph it. I'll put a 0 on here. Negative 2 is a little to the left of that. And our graph, we do an open circle because it doesn't include negative 2, and it's things less than negative 2. So we have to go to the left. So we shade to the left. And there's the graph of the solution. Moving to the next example, looks like we still have a distributive property to do here. So we got 6n minus 6 is less than or equal to 15. Negative times a negative here is plus 9n. We're going to go ahead and solve. There's a couple different ways to go here. I like my variable to be on the left. So I'm going to get my variable on the left. I'm going to do that by subtracting 9n from both sides. Some people prefer to have the variable positive, and that's also okay. And if you do it correctly, you'll still end up with the correct answer. So now we have negative 3n minus 6 is less than or equal to 15, because that's 0. And now we will add 6 to both sides, which gives us negative 3n is less than or equal to 21. And to finish, we need to divide both sides by negative 3. And when we multiply or divide both sides of an inequality by a negative, we have to switch the direction of the sign. Just switch the direction. We still keep it in with the or equal to underneath. And this is negative 7. We can graph that. I'll put it to the side here a little bit. We'll put 0 here, negative 7 somewhere to the left of it. I don't put everything in there, all the numbers. So this time, we draw a circle around negative 7, and we're going to fill it in because it includes negative 7. And its number is greater than that, so we fill to the right. I'll scroll up here. Actually, scroll down. Another one to solve. More distributive property. Negative 35 plus 10x plus, and we have distributive property again, 3 minus 3x is greater than negative 13 plus 7x. We'll go ahead and continue simplifying this left side for now. We'll add some like terms. Let's start with the x's. So we have a 10x and a negative 3x. So that's 7x. We can combine the negative 35 and the 3. That's negative 32 is greater than negative 13 plus 7x. We'll go ahead and get the variables to the left side, so I'll subtract 7x from both sides. And we run into something kind of interesting here. The x's cancel completely, and we're left with negative 32 is greater than negative 13. So that's different. And it's not even true. Negative 32 is not greater than negative 13. This is a false statement. So If we work through an inequality question and get a false statement, that means there is no solution. So there is no value of x that we could plug in here that will ever make that inequality true. That's what that answer means. While we're at it, let's go ahead and mention something else. If you solve an inequality, or actually even an equation, and you get to something that's always true, like 4 is less than or equal to 12. If we get something like that, that's always true. If you get something that's always true, then you'll end up with an answer that's all real numbers. I know that wasn't a full example there, but just to throw that in there, if you solve an inequality and you get something that's true, the answer is all real numbers. All right, this last one here. Looks like we have a negative to distribute. So we have negative 6k plus 12 is greater than, this negative gets distributed, negative 6k minus 8. Look at that, we're going to have one that we just mentioned. Let's get all the k's to the left side. So we add 6k to both sides. Up, k's are completely gone. And we are left with 12 is greater than negative 8. And from what we just learned 29 seconds ago, if we get something that is always true, our answer is all real numbers. Which means we can choose any value of k. I could choose 5 or negative 8 or 16.93, plug it in, and I would have a true inequality. And there you have the lesson on solving inequalities. Oh, we should go back. I forgot we were supposed to graph our solutions. So for this third one, to graph the solution, we would make our number line, put a 0, and we would not shade anything in because there's no solution. And for this one, we can put a 0 in there, and it's all real numbers. So we would shade everything. Sometimes when everything's shaded, it's hard to tell because it looks like everything else, but that's what you do for all real numbers.